All right, we're on to chapter 6. Isn't that exciting?
I guess so.
Well, you should be excited. You're not excited?
Yeah, I guess I'm excited. It's been hard though.
Well, you're very smart and you've learned a lot, haven't you?
I've learned a few things.
Okay, very good. Hopefully in this chapter, you can learn about oxidation and reduction. Now, oxidation and reduction is the second kind of chemical reaction that we're going to kind of talk to you about. Now, the last one was called a metathesis reaction, where we were combining chemicals together that were in solution, aqueous in solution. And we'll still work with a lot with stuff in solution. And there was a general pattern. Do you remember the pattern?
For what?
For the metathesis reaction.
Yeah, it was like A, B, C, D, something like that.
Okay, so yeah, AB and CD were combined. And then what were the products?
Let's see. A had to go with D.
That's right. And what had to be left?
B with C.
Or was it C with B?
Yeah, that's right.
Good. So what we're seeing here is these two ionic compounds that were dissolved in solution, or acid-base in some scenarios, right, were combined in such a way that they would trade partners, and then one would either be a precipitate, one would be could be a gas, or could be water in the case of acid-base acid-base neutralization reaction. Okay, so this time our reactions are not going to be anions and cations changing partners, but they're going to be where one species actually gives or takes an electron from the other. Okay, and we have fancy words for these kinds of reactions. We call them oxidation reduction reactions, or reduction oxidation is fine, or even shorter, you can say redox reactions, redox. Now, we don't just say oxidation reaction or just reduction reaction, because you can't have one without the other. Okay, it involves two steps or two species. One, for example, sodium losing an electron, right? This is an oxidative half reaction, we call it. Okay, it's not a complete reaction because electrons just can't go into space like this, all right? So sodium will form an ion and release an electron, while chlorine will gain an electron and form the chloride ion and become a negative charge. And the net reaction is sodium metal, chlorine gas coming together to form sodium ions and chloride ions, and sodium chloride is the result. And remember when we saw that chemical reaction a while back where we put some sodium into a flask of green gas? Okay, so oxidation is the fancy word for a process in which an element loses an electron. Okay, and when an element gains an electron, what do we call it?
Reduction.
That's right. Very good. And so a redox reaction is when one species gains an electron and one species loses an electron. Okay, or an electron transfer reaction. Okay, very good. Now we also have ways to refer to compounds that are in redox reactions as either the oxidizing agent or the reducing agent. Okay, now here, let's see if you remember the previous slide. Chlorine is gaining electron. What does that mean that chlorine is doing?
It's being reduced.
That's right, it's being reduced. It's gaining an electron. If it's reduced, it must have gained that electron from someone else or from some other species. And that species, it had to have taken that electron away or oxidized that species. So that makes chlorine, in the process of gaining an electron, an oxidizing agent because it's oxidizing some other species. And sodium gains an electron here, becomes oxidized itself, but because that electron had to go somewhere, we call sodium a reducing agent because it leaves that electron with some other compound. So it reduces that compound. Okay.
That's kind of confusing.
Yeah, it is not straightforward. Or, well, it takes a little bit of thinking. If you hold still, though, and just remember that oxidizing is losing electrons and reduction is gaining electrons, then it becomes easier. And I have a little way to help us remember that. And you might have one from your previous classes as well, previous experience with chemistry. We have this one, oil rig, where this means oxidation is loss of electrons and reduction is gain of electrons.
Okay.
You've seen one of those before?
I've never heard of oil rig, but I heard about a lion, Leo the lion.
Oh yeah, Leo the lion. What do you remember that one?
Leo said rar or something like that.
Okay, it's actually this is another way of remembering that the loss of electrons is oxidation. Loss of electrons is oxidation. Leo says gur, gain of electrons, reduction. So Leo the lion says gur, that's loss of electrons, oxidation, gain of electrons, reduction. Oil rig, as we already explained, oxidation is loss and reduction is gain. Okay, if you just remember that part and then you think, okay, this species here is losing an electron, it's becoming oxidized. Whoever it's losing that electron to, from their perspective, it is the reducing agent. Sodium is the reducing agent for whatever. So let's look at whole reactions here so we can kind of figure out what's going on. Here we have zinc and platinum ions, zinc and platinum ions, and the result of this reaction is that platinum no longer has a charge, but zinc has the charge. So here, can you tell me how many protons zinc has and how many electrons this species has?
Yeah, if you show me the periodic table.
All right. So let's bring up the periodic table. Where is it? Okay, here's the periodic table, and here's zinc.
So 30 electrons and 30 protons for, I can't see it.
Yeah, let's get it for you here. Oof. Disobedient periodic table. Okay.
Yeah, 30 protons, 30 electrons.
Okay, so let's look over here. As a product, what has happened to the zinc?
Plus 2, it lost 2 electrons.
Very good, very good. And can you tell who it lost those electrons to?
The platinum ion. Platinum ion took those 2 electrons and became platinum metal.
Very good. Platinum solid, right? And that's just metallic. This is the ion form in aqueous solution, and this is the solid. Okay, very good. So, which species then functions as the oxidizing agent? Which one functions as the oxidizing agent? Well, we can think about this a couple ways. We can think about who was, first we want to find out who was oxidized and who was reduced. Do you know who was oxidized?
Let's see, oxidation is loss. Oxidation is loss. Zinc lost electrons. So zinc was oxidized.
Very good. So if zinc was oxidized, that means that the other component, platinum ion, right here, right, was reduced.
Yeah.
Okay, so if this was reduced, who reduced it?
The zinc reduced it, so the zinc was the reducing agent?
Very good. Zinc was the reducing agent. It reduced platinum. Therefore, that makes platinum ion here the what?
Oxidizing agent.
Very good. So our answer is C. Fabulous. Here's one. I'll let the folks at home work on this one. Hopefully they can get it. You will look at it too. All right. I'm going to show the answer now. Push pause if you don't have it yet. Which species gets oxidized in this reaction?
Zinc solid, so D.
Very good. Zinc is being oxidized. It lost 2 electrons. All right, which species is the oxidizing agent and which gets reduced? All right, everybody take a chance to answer this one. Push pause if you haven't answered it yet. All right, we're going to tell you the answer now.
Who, me?
Yeah, Fred, give it a shot.
Well, I'm kind of confused because it says oxidizing agent and which gets reduced. Wouldn't that be the same thing? Because if it was the oxidizing agent, it would be reduced itself, right?
That is right. That is right. Good. So that narrows it down to B or D. I guess you could also narrow it down. No, B or E. B or E. Manganese is the no. Sorry, B or D. B or D. E is manganese and manganese ion. Okay, so B or D, and let's see, what is manganese doing? That's easy to see.
Manganese is being oxidized.
Very good. So which species is the oxidizing agent? So manganese was oxidized. It wasn't reduced. So that means that the H plus here was reduced.
Yeah. So it has to be B or C. So it has to be B.
Very good. Excellent job. We knew that manganese was oxidized. Therefore, we knew that H plus was reduced. And that's what I was asking for. We knew that manganese was oxidized. So we knew that manganese was the reducing agent. And then we knew that this one then was the oxidizing agent. Okay. Excellent job. So remember, oxidation and reduction reactions always occur together. And the total number of electrons lost by one species has to equal this amount that's gained by other or different species, right? Yeah, electrons don't just go into thin air, okay? Now, it becomes important for us to be able to look at chemical reactions and determine whether they're redox reactions or not. Redox. Now, redox is our conjuncted word for reduction oxidation or oxidation reduction, right? And to be able to look and see if they're redox reactions, we have to be able to look and see if any species has gained or lost electrons. So if we look at something, a simple reaction like this, right? If we look at a simple reaction like this, and we say that our products look like that, right? Is this a redox reaction?
Well, I can see copper lost electrons and gold gained electrons.
Yeah. So it's easy to see, isn't it? It's easy to see because you can see that copper, how many electrons does this species have?
I can't remember. Give me your periodic table again.
All right. Copper?
29.
All right, yeah. So copper metal has 29 electrons here, 29 protons, 29 electrons. Over here, how many protons?
29.
But how many electrons?
31. Oh, no, 27.
27, right? The plus 2 doesn't mean that we've added 2 electrons. It means we have an imbalance and that there's more protons than electrons. And we didn't gain protons, it's still copper, so we must have lost electrons. So yeah, we can look at some of these, and if somebody says, is this a redox reaction, we can say yes, right? Because we can see that it gained or lost electrons. However, we can also be given chemical reactions like this. I'm not going to take the time to balance this, but if I get, this needs to be CH4. If I get a chemical reaction like this, is this a redox reaction?
It's a combustion reaction. I remember that.
Oh, right. You're right. It is a combustion reaction. We talked about this, right? Taking something that has mostly carbon and hydrogen and oxygen and producing carbon dioxide and water. That's a combustion reaction. But it turns out that it is also a redox reaction. They can be both, right? Combustion isn't limited to that. So how can we tell? We can't see what electron density is, who's gained and who's lost electrons. So we need to be able to look at compounds with the elements within compounds and identify oxidation numbers, we call them, oxidation numbers. Now this is the method that we use to see whether or not an element within a compound, and therefore the compound itself, is either oxidized or reduced, okay? So these are the rules for identifying those oxidation numbers. And the oxidation number has to do with either having more or less electron density. So if it's a free element by itself, any element in the periodic table, right, if it's just iron, for example, then it has 26 protons, 26 electrons, and there's no extra or missing electron density. So the oxidation number is always 0. So with an elemental compound, the oxidation number is always 0. Again, it has to do with how much electron density, the movement of electron density gaining or losing, and also how much, and so therefore you can, if you know how many electrons and how many protons are on a species, then you can know the oxidation number. So free element, always 0. If it's a simple ion, like magnesium plus 2, if it's a simple ion like magnesium plus 2, then it's the charge on the ion. So plus 2 is the charge and plus 2 is the oxidation number. Cl minus, -1, monatomic, right? Means one atom, simple monatomic ion. Therefore, the oxidation number for this species is -1 as well. All right? So those two rules are pretty obvious. There's nothing new that we've introduced. In fact, we've worked a lot so far about how to identify the ions within ionic compounds, right? So if I give you an ionic compound like this one, okay, Cr is chromium. Do you know what the name of this compound would be?
Chromium bromide. Wait, is there more?
Well, a little bit. What else do we need there?
Is chromium a transition metal?
Yes, it is.
Okay, chromium 2 bromide. The 2 tells us the charge on the chromium ion.
That's right. Good. So chromium 2 bromide there. We can look at the elements here and pick out the ions that they're made of, right? Chromium ion and 2 of these bromide ions. And therefore, we can look at the chromium itself and say what the oxidation number is. It is the +2. The bromine oxidation number for these bromines are, both of them are a -1. Okay? So, nothing terribly new there. Free element, it's 0. Monatomic single atom ions, whatever their charge is, that's what the oxidation number is. Fluorine. Fluorine, and we'll see, look at fluorine on the periodic table here where it's at. It's a halogen, right? Fluorine is always a -1 when it's with the compounds. Group 1A metals are always +1.
Group 2 must be +2. That makes sense because if they're in ionic compounds, we already know their charge, therefore their oxidation number is the same, right?
That's right. That's right. So that's pretty straightforward. Any compound that contains group 1 metals, they're +1 oxidation number, group 2, +2 oxidation number. Hydrogen in its compound is +1. All right, hydrogen is +1.
Well, why isn't it just that group metal, group 1A, are all +1? Why does it say group metals there and then hydrogen later on in group 6?
That's a very good question. That's a very good question. And I'll tell you why. Okay. I was going to tell you this later, but I'll tell you right now. Sometimes in compounds, you see conflicts between these rules. And if there's ever a conflict between the rule, what we need to do is we need to accept the rule that's the highest or closest to the top on this list. They take priority over each other if there's ever a conflict. And so you see here, group 1 metals are +1 always, and group 1 or hydrogen will be +1. But there are some scenarios in which there are other elements that would take precedent over them. Okay? All right. And if that didn't make sense, hold on and I'll re-explain it a little bit later. Okay.
I think it made sense.
Oh, good for you. Big boy.
Thank you.
All right. So, rule 7, oxygen in its compounds is always a -2. And again, that's not a big surprise because it likes to lose 2 electrons. All right. Rule 8, the sum of all the oxidation numbers in a compound. So all the elements' oxidation numbers in the compound, they have to add up to whatever the charge is on that compound. Okay? So here we said that the chromium was +2 and that each bromine was -1, and there's no charge on this species. And that makes sense because this oxidation number is a -2 and there's 2 -1s there. So there's no oxidation number. All right? So the sum of the oxidation numbers is always are always equal to whatever the charge is, all right? So let's look at this one, for example, NH4 plus, all right? The oxidation number on the hydrogen is what?
The rule says +1, rule 6.
That's right, +1. And there's 4 of them, right? 4 of them. So there must be 4 of these +1s. So I'm going to say +4 from the nitrogen, or from the hydrogens. And whatever the nitrogen is, if I add it to that +4, the sum has to equal whatever the charge is. So it's +1. So then I can find out what the nitrogen is, even though there's no rule about nitrogen there.
Okay.
I can find out what the charge of the nitrogen is. Or sorry, the oxidation number of the nitrogen. So in this case, it has to be a -3. Nitrogen's a -3. Each one of these hydrogens a +4, and that's why we end up with a +1 net charge. So the charge on the species goes here. So let's look really quick at another example. Sodium chloride, right? Do you know the oxidation number on the sodium?
Well, you said that the charge on that ion is the oxidation number, so is it +1?
That's right. Sodium's a +1. And do you know what the charge is on the chloride?
-1.
Very good, -1. And if I add those two together, they have to equal, what's the charge on sodium chloride?
There's no charge.
That's right. So they have to equal 0. And so you see that that occurs too. And it will always occur with ionic compounds, simple monatomic ions in the ionic compounds specifically, because an ionic compound doesn't have a charge, right? If it has a charge, it's not an ionic compound, it's a polyatomic ion of some sort. Okay, very good. So this is the last one here, the oxidation number of group 7, that's our halogens right here, fluorine, chlorine, bromine, iodine, right? The oxidation number of group 7 is -1, except if an element is combined with one having a higher electronegativity. You don't have to worry too much about this rule if that doesn't quite make sense to you. I mean, yeah, don't worry about that last part of the rule. Electronegativity increases as you go to the right and up, and we haven't talked about that we haven't talked about that before, so if you haven't heard that before, it's not going to be helpful to you, but it doesn't need to be helpful. You'll see that we'll be able to figure things out without that last little bit. Essentially from this, we see that group 7, fluorine, chlorine, bromine, and iodine, all have a -1 oxidation number. Okay. Now, as I mentioned, if there's a conflict between two rules, you apply the rule with the lower number, the one up here, and ignore the conflicting rule. All right? Okay. And okay, yeah, there we go. All right, so let's assign oxidation states to all the atoms in this compound. Okay? So this is an ionic compound, simple monatomic ions, so it's pretty straightforward. The charge on the iron in this is what?
Well, if I use the reverse rule, it's +3.
You mean the reverse crisscross rule?
Yeah.
So, right, let's remind folks at home about that. Right, you can go like this and like that, and you can see that, well, this is a combination between an iron +3 ion and oxygen with a 2- charge, right? Those two ions. So, yeah, that's right. That's the answer. Because it's a simple monatomic, or an ionic compound that's made of simple monatomic ions, it's just the oxidation number of the elements are the charges on those ions. All right, what about this one here? Na2CO3, what's the oxidation? Oh, now, one thing that we want to remind ourselves and see is that the iron's oxidation number was not the sum of the oxidation numbers on the iron. It wasn't a +6. All we're interested in when we're asking the oxidation state of the different atoms is the individual atoms, each one, what the oxidation state is. So, one more thing we should look at here is see how the +3 charge here, and there were 2 of those, gives us a total of +6. 3 of the minus 2, that's a minus 6, and the sum of those two adds up to no charge on the compound.
Yeah, you said that before.
Okay, yeah, right. I'm just making sure we got it. Okay, so Na2CO3. Na2CO3. What do you know? Do you know the oxidation number on Na?
Yeah, that's +1. This is an ionic compound too.
Oh, yeah, right. So sodium has to have a +1. All right. Now, what about the carbonate?
Carbonate's -2.
Yeah, but do we know the oxidation number on the carbon or on the oxygen specifically? Because you can't just have the oxidation number of a polyatomic, the whole polyatomic ion.
Oh. Well, oxygen was -2. That's what that rule said.
Very good. Oxygen's a -2. So if I have sodium with a +1, and I look at this compound here, Na2CO3, right? Oxygen's a -2, so that's 3 of those -2s, so that's a -6 altogether. And the sodium had a +1, and there's 2 of the +1s, so that's a +2. So the +2 of the sodium, plus whatever the carbon is, plus the contribution from the 3 oxygens, has to equal what?
0, because there's no charge.
That's right, there's no charge here. It has to equal 0. So by comparing what we do know, the oxidation state of the sodium, the oxidation state of the oxygen, then we can find out what the oxidation number for the carbon here is, and so the carbon must be what?
-1.
Very good. +1, isn't it?
Oh, +1.
That's right, +1. So we have a +3 and a -3, that equals 0. So the answer is sodium has a +1, oxygen has a -2, and the carbon had a +1 also. Very good. Oops, did we do that wrong?
I don't know.
Sodium has a +1. Each one of those has a +1. Oh, sodium has a +1, so there's a +2 there. Oxygen has a -2. Oh, this isn't 3, that's 6. Each one has a -2. That's -6.
Oh, yeah.
So this carbon here has to be a +4. Very good. All right. Let's see if we can get the next one. Do you know the name of this compound?
I remember OH- is hydroxide.
Very good.
V, I don't know what V is.
Let's look it up on the periodic table here.
I see it, vanadium.
All right, good. Vanadium right there. Good. Kind of small there, but you got good eyes. That's good.
Yeah.
Okay, so what's it called?
Vanadium, it was a transition metal?
Yep, it was a transmission metal right here.
So vanadium 3 hydroxide?
Very good. Vanadium 3 hydroxide. So let's think about the oxidation numbers on the different elements. What do we know about vanadium oxidation number?
Well, there's not a rule, but because it's an ionic compound, the vanadium is going to have an oxidation state of +3 because that's its charge.
Very good. So vanadium is a +3, and if we look at vanadium coming together with 3 hydroxides, right? Vanadium is a +3. Whoops, +3. There we go. Oxygen is what?
Oxygen is a -2.
That's right. Oxygen's a -2, but we have 3 of them, so that's a -6 altogether. So we got a +3 plus a -6 plus the contribution from the hydrogens has to equal what?
There's no charge, so 0.
Very good. So what is the hydrogen?
+3.
Yep. And that matches with our rules as well. So vanadium is +3. No, sorry, not +3. It's +3 from here. But what is the hydrogen's contribution, or each hydrogen?
Each hydrogen's just +1.
That's right. So vanadium's the +3, oxygen's the -2, and hydrogen is +1 each because there's 3 hydrogen, 3 oxygen. Okay, did you follow that?
Yeah.
Very good. So, what in the world is this thing?
I was looking just in case. I saw that Cr2O7 is dichromate. So this is potassium dichromate.
All right, very good. Okay, so how do we identify what the oxidation numbers are?
Well, I had this, I remember this now from high school, I think. And can you separate the cations from the anions? Because I feel like that's what we did.
Yeah, that's not a problem. So you want to separate them?
I like that better.
All right, so if we just say we have a potassium ion and we have Cr2O7, the dichromate ion. Do you know the charge on the dichromate ion?
It's on the polyatomic ion chart. Let me look.
Wait, you don't need to look yet because you can tell just by looking here.
Oh, because potassium's +1, so dichromate must be -2.
That's right. Very good. So dichromate -2 here. I can solve this. I can identify the oxidation number here very easily, and I can do this one all by itself because now it has that charge there. So we don't have any rules about chromium, but we have a rule about oxygen, right? What's the rule about oxygen?
-2.
Very good. So oxygen's going to be a -2, and that's a total of a -14 that it brings to this. And if I add the chromium's contribution to the oxygen's, what is the sum?
It's going to be -2 here because it has -2 charge.
Very good. So the chromium contribution must be what?
+14. Plus
What?
+16?
Very good. Plus 16. Well, no, almost. Plus what?
Oh, +12.
Plus 12. Very good. Plus 12. Plus 12. So 12 minus the 14 equals our -2. Now, plus 12 is the contribution by the chromate, or the chromium, but there's 2 of them. So what does that mean?
I'm not sure.
Well, remember, oxygen's oxidation number is not -14. It's what?
Oh, it's -2.
That's right, it's -2. And there's 7 of them, so it's -14. Chromium here is a what?
Not a +12. It's a +6.
That's right. So chromium ends up having the +6 charge, and oxygen is going to have our -2 charge, and potassium over here has a +1 oxidation state. Okay, very good. All right, here's kind of a tricky one. What's the oxidation number of fluorine in F2O? Fluorine in F2O.
Oxygen's -2. Fluorine +1. Is that? I think that's okay.
All right. Do you remember that there was a rule for fluorine, though?
There was?
Yeah, let's go back and look at the rules really quick. Here, we see that number 3 is that fluorine compound is a -1. Oxygen's rule down here is that it's a -2.
Well, that doesn't make sense because you can't have both of those being minus without a charge on it, right?
That's right. So which rule do we have to contradict?
We have to contradict. We have to keep the rule that's higher on the list, top of the list.
Very good. So which one is that?
Was that the fluorine one?
Yeah, the fluorine one was higher on that list. The oxygen was a little bit lower.
So what was the fluorine one again?
It said that fluorine is always a -1. So if fluorine in F2O is contributing a -1, each one of those, or those 2 contributions equal +2. So that plus whatever the oxygen is has to equal what?
Has to equal 0.
Very good. Has to equal 0 because there's no charge here. And oxygen we thought was a -2, but we're wrong. But we can see here that it must be a what? Whoops, this is not a +2. This is a -2, right? -1, -2. It must be what?
Must be a +2?
That's right. So oxygen is a +2.
Why is it a +2 there?
Well, that's the way the cookie crumbles. Oxygen can be a little flexible. Carbon is the most flexible element in terms of its different oxidation. Well, not necessarily, but there are elements that are more flexible than others. And oxygen can be flexible at times, and here we see that flexibility. So the oxygen's oxidation number is -2, and each fluorine is a -1. So the answer is A. Okay. Oxidation number of phosphorus in H3PO3. All right, I think this is a good one for you guys, you folks, to try it at home. Why don't you take a second, try to get the answer. Push pause. Okay, I'm going to show you the answer. Hope you're ready. Okay, the answer is +3.
That's the phosphorus?
Yeah, +3. Should we do that one together?
Yeah, show us how you got that.
All right, so we got H3PO3. We look at our rules. What was the rule for hydrogen?
+1.
That's right. So each hydrogen's a +1. There's 3 of them, so that contributes a total of +3. Because the contribution from the hydrogen plus the contribution from the phosphorus plus the contribution from the oxygen all adds up to equal what the charge is here, which is 0. So the phosphorus, what does it contribute?
What was the rule about the phosphorus?
We didn't have a rule. We didn't have a rule about phosphorus, so we don't know. So that's a good point. We have to kind of go somewhere else first. Oxygen, we had a rule.
Yeah, -2.
Very good. -2. Each one's a -2. Therefore, a total of -6. Okay. So now we can see that the phosphorus must be what?
A +3?
Well, this slot needs to fill up a +3, and because there is just one phosphorus, then yes, it ends up being +3. Very good. Excellent. How about this one? What's the oxidation number of oxygen atoms in H2O2?
This is easy.
Oh, is it?
Yeah.
Okay. You take the time to do it at home. Let's see if you get the right answer. Okay, did you get it?
I got it.
What is it?
-2. Oh, -1? What?
Yeah, -1. Okay. So why did you think it was -2?
Because the oxygen rule is -2.
All right, let's take a look at this one. H2O2. What was the rule for hydrogen?
+1.
+1. So each one's +1, so a total of +2 contributed there. Plus, what's the rule for oxygen?
-2.
-2, with a total of -4 here, right? But the sum of these is supposed to equal, is there any charge on the H2O2?
No. So 0?
Yeah, the sum is supposed to equal 0. So we have a problem, right? 2 rules aren't compatible, so we have to get rid of one of the rules. Which one are we going to get rid of?
I guess the hydrogen was higher on the list than the oxygen, so we'll have to change the oxygen.
That's right, we'll have to change the oxygen. So if we change the oxygen, the sum of those oxygens has to be -2, right? That doesn't mean oxygen is -2. That means just the sum of all those oxygens has to be -2. And each oxygen then ends up being just a -1.
Okay.
All right, good job. All right, so now can we look at this reaction here and find out which one of these is a redox reaction?
Potassium ion, chloride ion. That's not a redox, right? Because A is not a redox because they start off as charged species and then they come together. They're not charged when they're together, but the oxidation numbers are the same.
That's right. So what we're looking for is the change in oxidation number going from left to right.
B is a redox reaction.
B's redox reaction?
Yeah, I can tell right now because copper has no charge, oxidation number of 0 initially.
That's right. If it's an element by itself, that's 0.
And then over there it has minus, where's sulfur again?
Here's the periodic table. Sulfur's right here.
Sulfur has a -2. So copper has a +2 there, +2 charge.
Very good. Copper has a +2 charge here. So B is our answer. We can see that copper has what? Been oxidized or reduced?
It had no charge, and then it had a plus charge. It got that plus charge because it had fewer electrons. So it lost electrons. Loss of electrons, loss of Leo, loss of electrons is oxidation. Copper was oxidized.
Very good. Excellent. Now, you can see that this one here, this reaction C, is, well, can you tell what kind of reaction it is?
It looks like the old stuff. Potassium ion there, potassium ion over on the right, barium on the left, barium on the right.
Very good, exactly. So this is a metathesis reaction, right? Permanganate, permanganate, barium, barium. Good.
So is that one.
Yes, it is also metathesis. Just what is HCl?
HCl is an acid.
That's right. H, hydrogen. Remember what it's named?
Hydrochloric acid.
Very good. So this is an acid-base reaction. Okay, excellent work. All right. What is the oxidizing agent in this reaction?
How can we tell?
Well, we need to be able to look at oxidation numbers, right?
Oh, okay. So I need to find the oxidation numbers for everything?
Well, the more you find, the more confident you'll be. But if you look at this compound here, the H, S, and the O, and try to find out where it winds up over here on the product side, right? Here's the sulfur and there's the sulfur. So we can look and see if that sulfur has changed oxidation numbers. We can also look, and then that would make this either the oxidizing agent or the reducing agent. You could also look at the carbon, right? Because the carbon only ends up in one spot. So we can look at the sulfur and the carbon and see what their oxidation number is.
So what's the oxidation number of the sulfur in the first compound?
Right here?
Yeah.
Well, let's find out, right? How do we find out?
Hydrogen was +1. Oxygen is -2. I don't know the rule for sulfur, but we can add it together.
H2SO3. Hydrogen is +1, oxygen is -2. There's 2 of the hydrogen, so that's a +2 contribution by the hydrogen. And that's plus whatever the contribution is by the sulfur. Plus, what's the contribution by the 3 oxygen?
-6.
-6. Very good. And what's the sum supposed to be?
0.
That's right, there's no charge. That 2 there is for that minus. So the sulfur here must be a +4, is that right? Okay.
So is the answer, wait, did that tell us anything?
Well, that just told us what the oxidation number of the sulfur was on the left. And now we have to find out what the oxidation number of the sulfur on the right is. SO4, 2 minus. What's the oxidation number of the sulfur here?
Oxygen's -2. 4 of those is -8. -8 plus whatever that is has to equal the -2.
Very good, -2, so that's a +6, isn't it?
+6, yeah. Okay, so what does that mean? Sulfur was a +4, and now it's a +6. Is that what we're seeing?
That's right. Sulfur had an oxidation number of +4, and now it has an oxidation number of +6. So, did it gain electrons or lose electrons?
+4 +6. It lost electrons because it has more of a positive charge.
All right. Loss. Losing electrons, is that oxidation or reduction?
That's oxidation.
So does that make it the oxidizing agent?
Yeah.
Are you sure?
Wait, it was oxidized?
Yes, we saw that it was oxidized.
Oh, so that makes it the reducing agent. Good. So it's not A, so it's got to be B, right?
It does have to be B. Why does it have to be B?
Well, because that's the only one.
Well, it says that this is not a redox reaction.
But we saw that sulfur was oxidized, so that can't be right.
All right, very good. So it means that our carbonic acid here is our reducing agent, the reducing agent. Or sorry, the oxidizing agent, because it was reduced. Okay, excellent job. All right, what is the oxidizing agent in this reaction?
This is easy.
Why is it easy?
Well, because...
Wait, don't tell anybody. Let them do it at home. You guys take a look at this at home, and once you get the answer, Fred will tell us why he thought it was easy. And, you know, just because you think it's easy doesn't make it easy.
Yeah, I guess not. But it's easy to me.
You think it's easy to you, but you never know.
Yeah, you're right.
All right, so tell us, Fred, what do you think? What's the answer here?
Well, I see that chromium starts off at 0, and then it becomes, well, I guess I don't know what the number is there. Can we find out what the number is in the chromium?
All right, so Cr2O7, dichromate ion with a 2- charge. We don't know anything about the chromium, but we do know the oxygen's a -2. So each one of those oxygen contributes a -2 for a total of -14. The contribution by the chromium plus the -14 has to equal what?
-2. Oh yeah, we did this before. The chromium is a +6.
Very good, +6. So the chromium here, or the contribution is the 12 because there's 2 chromiums. So you remember from the last one that the chromium in the dichromate has an oxidation number of +6. Very good. So what does that mean? Is the oxidizing, or was chromium oxidized or reduced?
Chromium was oxidized.
Very good. Chromium was oxidized. It went from what to what?
0 to +6.
Very good. Then, what do we know about the oxidizing agent?
It had to be either the MnO4- or the H+. And I can see the H+ on water over there.
This one here?
Yeah, it's still just +1, just like it is over there.
Right here, right? Because it's +1, has a +1 charge on it. And here, -2 for oxygen, +1 for each hydrogen, right?
Yeah, it doesn't change. So it means that the oxidizing agent, the thing that caused chromium to be oxidized, is the MnO4-.
Very good. Excellent job. All right. What is being oxidized in this reaction? You want to take a stab at this one?
Yeah. So,
Wait, let's let the folks at home do it first.
okay. I'll take a nap, okay?
Well, we're not going to be done. It's not going to take that long. They can push pause. Okay. Fred. Oh.
Yeah. Okay. So this one here, I don't know. I haven't done it yet.
All right. Well, let's look. Let's look at the chlorine. That one, like, you know, we could look at a lot of things, and all of it would give us good information. But I see the ClO-. That looks pretty straightforward because ClO-, the oxygen's a -2. The chlorine plus the -2 has to equal that charge, -1. So the chlorine must be a what? Whoops, got that down there.
Yeah.
Cl, oxygen's a -2. Cl something, that plus the -2 has to equal -1. So does that make chlorine the +1?
Yeah.
And then we can look over here, ClO3-. Same thing, but oxygen -2 contributes to -6. That plus the -6 equals -1 again. So that this time it's a +5. So chlorine went from a +1 to a +5. Therefore, it was what? Oxidized or reduced?
It was oxidized.
That's right. +1 to a +5, it lost 4 electrons for every chlorine, right? Okay, then was it, it's being oxidized. So that's the answer, right? They're not asking for the oxidizing agent. Okay, very good. Now, this process of oxidation reduction, these redox reactions, lead to a new kind of chemical reaction, which we call a single displacement reaction. A single displacement reaction. In a single displacement reaction, you have, like is shown here, one element combining with an ion, and the element takes the electron from the ion. All right, simple changing from metallic, this element here is usually metallic or elemental, now becoming an ion, while this one was ionic and is now becoming an element. And this can happen also with a counter ion involved, where A, no charge, B is in an ionic compound, and now A becomes in that same ionic compound with B not having a charge. All right? And this happens because element A in this case, for example, has a stronger affinity for that electron than element B. So element A steals the electron from element B and gets that electron. And we call that the degree of activity. We say that B is more active because it wants to get rid of that electron more than A is. A wants to hold on to the electron, and that's why B let go of it. Okay? So we have what's called an activity series, which we'll look at, which tells us which elements are more active than others. And from that, we can predict whether chemical reactions will occur. Here's another example of this kind of single displacement reaction. Here we have metallic zinc, and I'll write the chemical reaction here for us. We have metallic zinc, and we're interacting it with copper ion. All right, metallic zinc and copper ion. Well, the zinc is more active, and so when copper, which has a +2 charge, interacts with zinc, the zinc is more active. The copper pulls those electrons from zinc, and the result is a zinc ion. And the copper gets those electrons and becomes elemental copper. Electroplating. I don't know if you've heard of electroplating, but sometimes you can electroplate material this way by bringing a less active species in the presence of a more active metal. The less active species will take the electrons from the more active metal. The more active metal will result in ions in solution, but the active or less active ion will become metallic on the surface there. Okay, very good. So here is our activity series.
I've seen that.
Oh yeah, where have you seen it?
It's on the back of the periodic table.
That's right, it's on the back of the periodic table. And it shows us the more active elements. Now, sometimes in a test question, you might not be provided with this specific activity series. You might be given one that's kind of flipped or whatever. So you kind of always have to look at it and see which end is which. And you can tell by looking at the side that has the gold, silver, copper. These are the coin elements, right? The elements that we make our metal, our money out of, right? Or our material that we don't want to corrode. And that's because these are not very active elements. Whereas down here, cesium, sodium, potassium, rubidium. Remember what happens when those come in contact with water?
Yeah, they explode.
Yeah, remember we saw that video? So down here are our more active elements, They would prefer not to be metallic. They want to be active and lose their electrons. Whereas if you have ionic gold or ionic silver or ionic copper, these species, ionic species that are very unreactive, inactive, will take electrons from whatever species they can and form their metallic elemental form. Okay, so we can look at this chemical reaction and predict the product based on the activity series. So let's take a look. Can you figure this out looking at the activity series?
I doubt it. I'm not very familiar with the activity series.
Well, let's look at it together. Here's the activity series, right? And what we want to do is look at our reaction and find our elements, zinc and copper, on this activity series.
Okay, I found them.
All right, there's copper, and where's zinc?
Zinc's down in the middle.
Okay, there's zinc. So what is going to want to happen here is zinc is what, more or less active?
I'm not sure.
Well, remember we said the ones down here, stuff like potassium, sodium, rubidium, right? Those are our more active species. So the top are less active.
So copper is less active. Zinc is more active.
That's right. And we're asking zinc to give up its electrons here, aren't we? Because zinc has the electrons and copper does not. Copper here in this species is a +2 charge. And if you didn't know that, well, I mean, we have to know that by now, right? You have to look at the polyatomic ion chart and find out that this is an ionic compound. So the products, theoretically, we could tell what the products would be. Products would be kind of like what we showed down here. Zinc interacting with the copper ion to form the zinc ion and the copper metal. Now, the activity series, does it suggest that that is going to want to occur?
I think so, because zinc is more active. It wants to give up its electrons. Copper wants to hold on to its electrons.
Very good. So we can predict the products and we say, yes, this reaction will occur because zinc is more active than copper. Okay, here's another one. Copper ions interacting with zinc sulfate. Single replacement reaction. The products, can you tell me what the products should be theoretically?
Zinc sulfate and, no, we have zinc. Copper sulfate and zinc metal?
That's right. Copper sulfate and zinc metal. Now, is this going to occur?
I don't think so. It's like just the opposite of what we just did. And we looked at the activity series and decided that that one did occur. So this one, I don't think is going to happen. But I'm not sure why.
Okay, you're right. It's not going to happen. And this is how we can tell using the activity series. We can see that copper ion is, well, copper here, up here, is less active than zinc. And so it doesn't want to get rid of its electrons as strongly as zinc wants to get rid of it. Now these are elements. They don't have needs or desires. When we say want, we're talking about how much stabilization will come to them upon gaining or losing an electron or two. Okay, so we say no reaction. This will not occur. All right, how about this one? Do you want to tell me the name of that compound?
Ag silver nitrate. Silver nitrate. Silver 1 nitrate.
Yes, silver 1 nitrate is a fine name. We can just call this one silver nitrate because silver is actually an element that, although it's here in the polyatomic ion, or sorry, the transition metals, it only forms a +1 charge. There might be some crazy compounds where it forms other charges, but not very frequently. Usually it only forms a +1 charge. So, what are our theoretical products?
Well, we're going to get the copper with the nitrate, and then the silver as a metal.
That's right, as a metal. Silver is what? Being oxidized or reduced?
If it gets the electrons, it's being reduced.
Very good. Copper being oxidized and silver nitrate is being reduced, specifically the silver ion here. Now, does this reaction occur?
Bring out the activity series.
Okay. We're comparing
silver and copper. Oh, silver and copper are close. Let's see. So silver is right above copper. Silver is less active. Copper is more active. So copper wants to give up the electrons. So here copper starts with the electrons. So yes, this will happen, and we'll get copper nitrate and silver metal.
That's right. Very good. This will happen because copper is what?
It'll happen because copper is more active.
That's right. Very good. How about this one? Solid magnesium and aqueous iron 3 chloride.
I guess it's just written differently.
That's right. They're not going to give us the equation. They want us to know about what's going on here.
Iron is a +3 charge. Magnesium. Can you show me the iron and the magnesium? Iron is less reactive than magnesium.
That's right.
I don't like that it says iron +2 over there.
Oh, you mean this here?
Yeah, because where's the iron plus 3?
That's a good point. That's a good point. And it will be slightly different, but it won't be that much different for this case. So what will we say? Iron is less active. Magnesium, that's not magnesium, that's manganese. Magnesium here is more active. So what?
Well, we're asking magnesium to be more active. So yeah, that's going to happen. And the products will be magnesium chloride and iron metal.
Very good. Magnesium chloride and iron metal. Excellent job. How about nickel, solid nickel, and aqueous sodium chloride?
Can I see the chart?
Sure.
Sodium, I see sodium, but I don't see nickel.
Okay. So, is there any way we can solve it?
No, we don't have it.
Well, do we know anything about nickel?
They make money from it.
Yeah, well, they used to at least, right? So we do know a little bit about nickel, right? We know that if they used to make money from it, that's an indication that what?
It doesn't corrode easy.
That's right. Or in other words, it's not very active. What about sodium? Do we know about it?
It's very active.
That's right. It's very active. We saw that as a metal, it blows up. So if we mixed solid nickel with sodium chloride, what are we asking it to do? Are we asking the nickel to give up electrons to sodium?
Yeah.
That's right. Nickel solid, we're asking it to give up electrons to sodium to form sodium solid. Do you think it's going to happen?
I don't think so.
That's right. We're not going to have that reaction occur because sodium is already more active. It's not going to want to it's not going to take electrons away from nickel. All right. Very good. We can also use the solubility rules, but if we don't have our activity table, we can also use a series of reactions like this to know relative activity of different elements. So here we have magnesium and zinc combining together, and if it says that all of these reactions occur, right, we can then rank the reactions or the elements in terms of activity. Look at the third one here. Which one is more active? Magnesium or zinc?
Well, we're asking, or I guess magnesium is what? It's okay, I can't tell.
Well, look at the charge. What's the
Oh yeah, magnesium 0, and over there it's +2. So it was losing electrons, and zinc was a +2 and went to a 0. So it's gaining electrons.
Very good. So we're learning that who is more active, zinc or magnesium?
Magnesium is more active because it gave up its electrons for zinc.
Very good. So we could write that down. Who's more active, magnesium or zinc? Magnesium is more reactive than zinc. Okay, what about this one up here?
Zinc is reacting with the hydrogen. Is that what's happening?
That's right. H+ ion here is becoming hydrogen gas.
So zinc is more reactive than the hydrogen?
That's right. Zinc is more reactive than the hydrogen. And what about this last one here?
Copper is less reactive than hydrogen. Hydrogen is more reactive than copper?
That's right. Hydrogen is more reactive than copper. So from our reactions there, we have our order of activity. Did you follow that?
I think so.
Very good. Okay, good work. That's it for Chapter 6.
Oh, not a lot of slides.
No, not much. See you later.
Bye.